That hiss you're hearing isn't my room. It isn't my interface, that's the sound of heat, or at least the amplified signal produced by heat. You're hearing billions of electrons whizzing around in the metal of my microphone. Pretty cool, right? Or maybe hot. Today, I'm going to show you where that hiss comes from, especially in the context of dynamic mics. We'll do a quick overview of how dynamic pickups work, and then we'll dig in and see why you might get poor noise performance with these puppies. And I'll show you a clean way to compare the performance of different dynamic mics so you can buy the best one for your needs. Welcome to Overengineered. Most people clicking on this video are probably aware, but for the uninitiated, here's a quick overview of dynamic mics. They're really just speakers running in reverse. With a speaker, you ram electrical current through a few loops of wire, and that produces a magnetic field. When you vary the current, you proportionally vary the strength of the field. Then you suspend the coil next to a strong permanent magnet, and hey presto, the coil moves exactly along with the input current, more or less. Pop an acoustically tuned diaphragm on the end to help the device move more air, and you've got a loudspeaker. A dynamic mic uses the exact same design, but now the air moves the diaphragm and coil through a magnetic field, inducing current exactly along with the air movement. We can amplify the electrical signal that shows up across the coil to produce an electrical analog to the original sound wave. A lot of people will tell you that dynamic mics are worse at longer range pickup. They'll say dynamics are only good for close range vocal work. They say the mic can't pick up soft sounds because the pickup is too heavy. In some respects, these folks have a point, but that point misses the nuance. If you're interested in catching only vocal frequencies, I'm here to tell you that a dynamic mic can usually beat the performance of other mic technologies at equivalent price, regardless of range or sound pressure level. But that's the topic for the next video. Stay tuned and subscribe if you want to learn more. Back in the 1920s, a few brilliant engineers at Bell Labs, working off theories proposed by Albert Einstein a few years earlier, discovered that everything with resistance has electrical noise too, even if no current flows. This noise arises from the unavoidable movement of charge carriers in the atoms that compose everything. If an object exists and has any amount of internal thermal energy, it'll produce electrical noise due to thermal motion of electrons. It follows this equation. Kb is the Boltzmann constant, while R is resistance, T is temperature, and delta F is the frequency range of the measurement, also called bandwidth. Obviously, increasing resistance, temperature, or bandwidth will increase the noise. Engineers call this white noise, which means it's evenly distributed across all frequencies akin to white light. So the frequency range across which you measure matters a lot. The typically accepted range of human hearing is 20 Hz to 20 kHz, but that's in a lab with a young subject. If you're older or have heard too many loud sounds in your life, that range can drop precipitously, with 12 kHz max for older people being pretty common. Also, your ears are far more attuned to the typical vocal range of 90 to 10,000 Hz than other frequencies, so sounds in this range have more apparent loudness. Because of these psychoacoustic effects, pure, unweighted noise measurements can be pretty misleading to the actual noise performance of audio systems in the real world. The white noise between 15 and 20 kHz takes up a quarter of the measured bandwidth, but is barely audible. So the audio industry uses a technique called A-weighting when discussing noise performance that attempts to account for this. Part of a family of curves set by an international standards committee, the A-weighting curve reduces the relevance of sounds with very low or high frequencies. You can integrate across it and divide by the bandwidth to learn that A-weighted, pure white noise is usually about 2 decibels below an unweighted noise measurement over the industry standard 20 kHz range. When looking at datasheets for mics and amps, it is important to notice this. You need to know if the noise is A-weighted or not when comparing figures. If the letter A or the word unweighted does not appear on the spec sheet anywhere, that's a red flag. If you must assume, though, it's standard practice to measure noise as A-weighted. The manufacturer has an incentive to use weighting because the number looks better on paper anyway. So this thermal noise thing affects microphones too, of all types. But a dynamic microphone has no active electronics, so manufacturers can usually get away without publishing noise specs. People walk away with the false belief that dynamic mics don't have self-noise, but that's folly.
But this is folly.
Now you know better. You know that the pickup coil, which is usually a very thin piece of wire, must have a non-zero resistance, and therefore a measurable amount of noise even with no current or room sound vibrating the diaphragm. And the resistance is usually pretty far from zero. An SM7B has 150 ohms of it. The Sennheiser E835 that I'm using to record this audio has 350 ohms. And the venerable Shure SM58 that's recorded many of history's best singers has 300 ohms output impedance. These numbers aren't exactly the coil resistance, but they're close enough to get a first order SNR estimate. So here's the key point summed up. Dynamic mics have self-noise too, just like condensers. But their self-noise comes from physics and can't be removed with clever circuit design. The mechanical mic design, chiefly the size, definitely can change noise performance, but you can't cheat the physics of thermal resistance. So the question is, how can we maximize the mic performance? At the end of the day, the only thing that matters about noise is the overall signal-to-noise ratio, or SNR, of the recording. Rephrased, that's the strength of your voice relative to the unavoidable white noise, the bane of electrical engineers everywhere. Noise can be injected at many places in the system, but signal is only ever injected at the microphone, so we start there. A dynamic mic has another critically important figure called sensitivity that we need to know about. This is almost always measured in millivolts per Pascal, which is the root mean square voltage you would see across the mic output when a sound at 94 decibels sound pressure level hits the diaphragm. This figure, combined with the impedance and some math, allows us to compute the theoretical peak SNR of the mic. I'll walk through a quick example here to show how you can compute theoretical peak SNR for a dynamic mic. First, we compute the thermal noise from the Johnson noise equation as shown on screen. Don't forget, the temperature is in kelvins, not degrees Fahrenheit. We convert this to dBu and subtract 2 decibels to aweight the result, which is usually but not always necessary. Read the datasheet. Then we convert the sensitivity to dBu if not already done, and simply subtract to find the SNR at 94 decibels SPL input. For quieter signals, adjust the SNR downward by the difference between 94 decibels SPL and the actual sound level. This is the theoretical best SNR your mic can ever produce. It'll never be better than this number, but it will likely be within a few decibels if you adhere to the advice in the next section of the video. So you're probably thinking, shut up about the math and just tell me if I need a Cloudlifter or not to make my SM7B sound good. The short answer is no if you have a high quality interface, and yes if you have a low cost one. But it's way more instructive to learn why and be able to compute the answer so you don't buy something you don't need. We already used the thermal noise equation to compute the mic's Johnson noise. And then we express this as an A-weighted dBu value, which happens to be the same spec that most interface and recorder manufacturers display for their preamps as the equivalent input noise, EIN. So all we need to do is combine the thermal noise and the manufacturer EIN to get our actual input noise. White noise sources like this are not correlated. They add in power, not voltage, so we combine their RMS values as a sum of squares. If the manufacturer states a specific input test resistor is used in the measurement, you can subtract the self-noise of that resistor here too. Then we square root the result and convert back to dBu to get our computed noise floor with the real mic. You can do this computation again with a different EIN to know if a better preamp will appreciably improve your performance. As an example, using my Sennheiser E835 mic, the math predicts a 7.4 dB improvement in SNR when switching from a low-quality -120 dBu interface to an inline JFET-based preamp with roughly -129 dBu equivalent input noise. That's a huge, noticeable improvement. Here's a side-by-side comparison showing a measured 7.4 decibel noise improvement with and without the inline JFET preamp. Note that these measurements were taken with a 320 ohm dummy source resistor to simulate a typical dynamic mic, which removes the effect of room noise. Gain was normalized between the preamps with a fixed power test source. As another example, if you had a Zoom F3 recorder with an EIN of -127 dBu, moving to the -129 dBu inline preamp improves the floor by only 1.2 decibels. That's a bit better, but probably not audible above the room noise floor and not worth the hassle of using it. It's also worth noting here that most inline preamps are not well specified, so your mileage may vary. But their circuits are so simple that they are pretty easy to rip off, and I'll use my engineer wild-ass guess skills to say that most will have between -126 dBu and -130 dBu noise improvement if you don't buy an absolute lemon. I used the $40 Amazon special Studio Man DPM1 in this test, but a Fethead or Cloudlifter would perform about the same. Perhaps a video explaining preamp design in more detail is in order. Let me know in the comments if that would interest you. The wisdom of the internet holds that the Shure SM7B is the king of voiceover and nothing else. The Reddit and GPT overlords say you can't use a dynamic mic at range, that a condenser is the only mic usable for boom distance. Big shocker here, the internet's wrong, and you absolutely can use a dynamic mic at range. There's nothing in a dynamic mic's datasheet that says it can't pick up distant sounds. Frequency response curves and polar patterns look similar to any cardioid mic of any technology. There is some reduced sensitivity to sound above 15 kHz with dynamic mics. That range is largely useless for voice work anyway, and a lot of people will cut that out with a low-pass filter in post. The thing that limits a mic's ability to hear at distance is SNR. The polar pattern matters too for echo rejection, but I'll argue that a cardioid pickup pattern is sufficient for most use cases at reasonable mic distances. Dynamic mics don't include an SNR figure on their datasheets because it depends strongly on the noise of the preamp. But I've already shown that using a cheap inline JFET preamp from Amazon achieves a very strong SNR. In fact, running through the math for my E835 mic and cheap inline preamp yields an SNR higher than almost any other microphone I could have purchased for a similar price, condenser or otherwise. The only sub $200 mic I could find with better SNR is the Rode NT1 at 80 decibels, which has no built-in pop filter, is far less robust, and would be very difficult to hold by hand or transport to the field. In fact, this entire video was recorded with a dynamic mic at a standard boom range of about 1.5 feet with no external processing besides a bit of EQ. Did you notice any noise? You probably heard the reverb of my poorly treated recording space, but I doubt you noticed the noise floor. A dynamic mic is actually not a bad choice at all for boom use in a low budget operation, assuming you use a good interface or inline preamp, and has the advantage of high durability and appearance when being handheld. Looks are important, and hand-holding a dynamic mic feels natural, while hand-holding a condenser is strange. Handling noise will almost certainly intrude on your recording in the latter case as well. A very strong case could be made that if you're limited to one microphone, it should be dynamic. You get better performance per dollar for a much more versatile device that you can handhold without looking like a doofus. With a decent preamp, it'll perform well on a boom too. There are definitely compelling reasons to use condensers for some jobs, but for most, the dynamic mic will serve you better. So now we know what a dynamic mic is, what thermal noise is, how to compute peak SNR, and how much an inline preamp can improve a dynamic mic's noise performance. We've also seen that a dynamic mic can perform very well at boom distance. I highly recommend using these formulas and referencing this video when you cross-shop microphones. You can compare dynamic to condenser head-to-head using the performance of your own interface equipment to see which will perform best. For dynamics, if you have a nice interface or recorder, you likely don't need a Fethead or Cloudlifter. With a lesser quality interface, an inline preamp is probably worth it. Condensers, however, are a different story, and you'll have to wait till the next video to see why the interface almost doesn't matter for those devices. Subscribe to stay informed for that. If you found this helpful, a like, comment, or share really helps my young channel. See you next time.